Hi everyone, and welcome to the latest webinar in association with Fibre Systems. My name's Keely Portway. I'm the editor of Fibre Systems and I'll be your moderator today. In terms of format, we've got 3 presentations from 3 fantastic speakers, after which we've got a live Q&A. Please feel free to send your questions in as you think of them. Don't wait till the end to send them in. We'll collate them and ask at the end. Just a few brief notes, housekeeping points. We have certificates of attendance available if you would like them. Please drop us an email at production@europascience.com to get your copy. And we also will have resources available throughout the webcast popping up on the toolbar at the bottom. If you'd like to download these, have a look at them as you're listening, please feel free to do that. So that brings us on to today's topic. AI workloads are shaping data center interconnect, pushing use cases out of the lab and more into regional, long haul, subsea, and increasingly scale across AI clusters. This is driving higher, faster speeds, it's driving denser fiber, and it's absolutely accelerating optical innovation with things like hollow core fiber, multicore fiber, and numerous other innovations. The question is whether the physical layer can keep pace. And I have 3 experts today to help me answer that question. I'm very delighted to introduce Mitch Simcoe, IP Optical Solutions Marketing at Ribbon Communications. We have Kevin Boll, Technical Director at Nextrom. And we have François Marcotte, Business Development Manager, High Speed Rates Testing at EXFO. So, without further ado, I'm going to hand over to our first speaker. Mitch, floor is yours.
Thanks so much, Keely. And let me just get my charts going here. Okay, well, good morning, good afternoon, everyone. Thanks for joining our session. I'm going to kind of kick off our session. And certainly welcome having a great panel of speakers here to talk about really exciting topic. Certainly something we're seeing in the news every single day. I don't think you could go a minute without hearing about something about AI, certainly. But from an optical perspective, there's some really big impacts that we're seeing from AI. When these hyperscalers are building out these new data centers to support AI, typically these data centers are consuming huge amounts of power and especially need water for cooling. And the result of this is the places they traditionally would have built data centers for the internet really are no longer sustainable to support those power and cooling needs. And we're starting to see now that data centers are really built in more rural areas. They can't put too many of these data centers in the same place because of these power requirements. They're being built further afield, and as a result, we need very high-speed connectivity to connect them. And that's certainly something, and optical kind of comes from 3 different areas. There's basically having optical connectivity within the rack inside the data center. There's connecting data centers within a campus, and then now what we're starting to see, which is building data centers, connecting them, across a metro regional area. And the term for that is called scale across. That's really the new trend. And again, the amount of bandwidth we're needing for this are into the terabits of bandwidth. So just huge amounts of capacity. Just to show kind of what that trend is. So traditionally, where data centers were built for the internet, they tended to be built in these primary, markets, such as Northern Virginia, such as obviously Silicon Valley, Phoenix, Dallas. What's happening now is any new data center is being built around these metros or again in more rural locations. I'm based here in Atlanta, Georgia, and our state is actually a hotspot for these new data centers, and they're not being built in downtown Atlanta. They're being built probably about a 250 kilometer radius around Atlanta, but you still need to connect that capacity back to that hub to get into, again, to connect those AI clusters together. Other regional areas we're seeing here in the US, places you wouldn't think of, places like Nebraska, Iowa, um, all kinds of, like I said, interesting rural places. And again, the challenge is they're building them there because, again, the real estate and the power is available. But the challenge is you need to connect those back to those main kind of hubs shown in the black dots, right? So that's really the opportunity from a optical perspective. And another result, and all of our panelists can comment on this, really is fiber construction's back, right? To support these huge construction, the fiber cables, the routes that were built again for the first generation of the internet no longer are really sufficient to handle this huge amounts of traffic as a result of AI. So lots of new fiber being built. Um, the other thing that's really important is diversity. Um, the folks building these data centers want to have as many routes to connect for backup because, basically if a cable were to be taken out, due to someone with a backhoe, you basically lose millions of dollars of revenue from that, those AI workflows in that data center. So they're looking for backup, they're looking for diverse routes. And I'm hearing things that it's not even a second. They're looking for third, fourth, fifth. Any kind of diversity is important. And again, where these data centers are being built, it really follows the power. And I work with a lot of utility companies, and they themselves, the challenge is them, and they have to step up and have the power capability to support this growth. So what are the considerations when you actually are building this optical network? So the first is, and no surprise, I mean, there's nothing new here, but this is even becoming bigger in the era of AI, is reducing capex and footprint, especially footprint, because now these data centers, pretty much everything I'm hearing, once they basically build one, it's full, like literally day one. That's how fast they're consuming this capacity. They're looking for lower power, even though our optical industry probably isn't the biggest contributor. Probably the biggest source of power is the GPUs, is the servers, and so on. But anything we can do as an industry to support that's important. And they're looking for simplified design. They build these data centers with pretty much building block kind of designs that they basically cookie cutter in different locations. The second thing, as I mentioned, is scalability, right? They're literally, when they build these data centers, they're pretty much full on day one. And so we're talking about terabits of bandwidth having to be supported day one. And again, to support, again, this growth in AI. And I don't think anyone can really forecast where AI is going. So, constantly pushing the edge in terms of capacity. Operations is really important, and certainly these networks are really built with both IP and optical layers. We'll kind of talk about those interactions a little bit later, but operations are really key. Really, the need to be able to have visibility to both the IP and optical layers together, really, really important. And we'll talk about some of the different options are in those architectures. And finally, what's really becoming important now is supply chain, right? And it's unfortunately sounding a little bit like COVID again. Basically, this AI demand is really sucking the demand of the entire tech industry. I just read an article. Those of you who are like anticipating buying a new iPhone, I just saw a thing, basically the cost of memory that's affecting the entire industry. But our friends at Apple, they're looking at basically much increased price of memory DRAM, and what was used to be $1,000 iPhone is probably going to cost $1,200 in the next generation, and that's just a result of supply chain. In the optical area, this too is starting to squeeze. Most of the big vendors now have basically announced you can't, if you placed an order for an optical equipment today, you won't get it for 18 months, right? So it's kind of sounding like COVID all over again. Big challenge. And so you really need supply chain resilience. You really need to have the ability to select multiple vendors for your optical equipment. And that's going to give you much more flexibility during this constrained period. So let's kind of go through a little bit of the architecture, a little bit of history. So traditionally, when optical networks were built, the traditional model was for vendors to build what's called an integrated transponder, basically building everything all together. That basically the optical pluggable or transceiver into the chassis, everything was built in one. It was all integrated together. And there's a lot of advantages for that. And for certain applications, it's still the advantage. But as we move to this new kind of AI era, it's no longer necessarily the best model. What we're moving to is what we call a thin transponder, where we take the optical transceiver out and deliver it as a pluggable. And that gives the market a much more flexibility because now you can pick different vendors to go for that pluggable that's separate from the chassis. And there's still quite a few people who are going, are going to what's called an IP over DDMM model, where they're actually skipping the optical transceiver and just basically buying the pluggable and putting that on their router. And that's still a common option. Um, but you can see really the value of having that separate pluggable. It has a real value. And one of the things that we've done, and I'll talk a little bit later, is an initiative called Optical Freedom, where we have multiple vendors for those pluggables. Many of the major vendors in the optical market typically make their own optical transceivers and they package them together. So it looks a little more like the integrated transponder. So you really don't get the flexibility that you get through a thin transponder model. So we'll talk a bit more about that a little bit later. And I think we posted really good white paper if you want to learn more about that model. So the shift to pluggables has been happening for a while. You can see back in 2024, about 70% of the market was pluggable versus 30% integrated. And over time, and this is courtesy of our friends at Omdia, basically say that's going to continue the trend, about 75 pluggable, 25 integrated. I've seen some other analysts even showing that this is even more aggressive moving to pluggable. So really the world is moving, to this pluggable world. And we at Ribbon have many ways to integrate this. We offer pluggables in, again, 4-inch ZR plus packaging. We recently introduced an 800 gig ZR plus. And these are really the power cost optimized. So this is really, again, to address the need to minimize the power consumption for these systems. So really, really important. And we have multiple vendors for these. So again, we're not stuck. We will really seek out the best vendor to ensure our customers can get a supply in this constrained environment. Just to compare the different options, again, the integrated transponders I mentioned to you, really not designed to support a multi-vendor interop. It's really single vendor, although its main application tends to be much more the long haul, ultra long haul, subsea kind of applications, which you really need the highest performance. It's going to have the highest cost and the lowest density, but because it's all integrated together, it's going to have the best ability to support layer one client aggregation, has the ability to separate optical from IP, and the best optical O&M. If I look at the other extreme, IP over DWDM, this is again where you buy pluggables and put that in your router. This is support multi-vendor interrupt. You can get your pluggable from multiple vendors. Is designed more for a metro regional. But you can see here where you really lose out is really the O&M. You can't support other clients. You don't have that true separation of IP optical, and you really don't get the great O&M. And so that's why the thin transponder, as you can see kind of in the middle, it really shows it's kind of the best of breed of both scenarios, really giving you both that multi-vendor interop, but also all the feature functionality of an integrated transponder. So this is why it's a model that's really starting to emerge, and it tends to be more cost effective than an integrated transponder and deliver higher density. Just the word a little bit, many of you may not know Ribbon. So we offer, basically our value is we are really that middle mile. We bridge both the last mile access back to the core, and we have a family of optical networking products through Apollo, IP routing through Neptune, and we continue to support voice solutions, which we've done over many years. And we actually have a multi-layer management platform through Muse and a AI apps platform through Acumen. So certainly something, if you're not familiar with us, check us out on our website. Again, I'm not going to go too depth into our solution, but we do have a wide range of solutions to support this thin transponder solution. We have an advanced DCI platform in the 9408, one of the highest density, so it really takes advantage of that thin transponder architecture. Basically, you can basically deploy it up to fully filled 800 gig optics in a 2RU. Basically, you can do 25.6 terabits in a 2RU packaging. So really one of the highest densities out there. We have a very powerful intelligent software platform called Muse that can support both IP, optical, and integration, give you that visibility. And we have a approach of really self-service. We empower our customers to really be able to do a lot of capability on their own, not having to go to third parties. And we built in a lot of new AI applications into this. And we have a scalable OLS, and that's important again when you get into this thin transponder market, when you need to go some additional distance and support all that traffic capacity. That's a product that we support in our 9458. Last thing I'll say, back to this optical freedom model. Again, we kind of talked about the three options, the router attached. So the router vendors basically will package their own pluggables into that. The optical vendors will again package their own and a standalone. And again, most system vendors will tie their own pluggables to their own equipment. And that, again, in this supply chain constraints is a challenge. And really our optical freedom approach lets you choose among multi-vendors for those pluggables. So we can give you the best, basically, support best in breed for, being able to secure supply during this AI boom. All right, and there's a blog if you want to learn a little bit more about that. And I think that is all I had, Keely, so I'm going to go back to you.
Thank you very much. Thank you, Mitch, for that great presentation there. It was really, really interesting to hear what you guys are up to and what's going on in the industry in which we all work. So thank you very much. I'm going to hand over now to Kevin. Kevin, would you like to take the floor?
Yeah, thank you. Hello, everyone. I'm Kevin Boll. I'm the technical director at Rosendahl Nextrom. We are a leading manufacturer of equipment for production of optical fibers. So I will be discussing more on the connection side, the fiber side, where we see the market going, both inter-DC and intra-DC. So I'll just share my... I hope you see this now. So if I talk overall on what's happening in the market as we see it, that clearly the requirements of AI and the increased bandwidth requirements for lower latency, just more and more data is driving from copper to glass. So the copper connections that were traditionally used either can't keep up with the transmission rates or the power is too high. In addition to that, there's more and more fibers, as Mitch talked about. The inter-DC connections require very huge amounts of data, so it's very high data very high fiber count cables connecting both internal to the campus and between the different data center campuses. If we look at I won't go in too much detail in this, but if we look at what's being used today versus into the future, today many of the connections, especially on the short connections, are either a passive or an active copper connection. And more those are moving towards a fiber-based solution. The advantages of this is the lower latency, the higher data transmission rate, and lower power consumption. And I'll talk about where I see one of the more interesting movements is the onboard or the near package movement to the co-packaged optics, where the optical fiber will be connected directly onto the chip itself. The advantage of this is that it's a much lower power consumption. So, and Mitch talked about the power being a large issue in the data center design. Moving the electrons through copper is much higher power requirement compared to an optical. And every time you have to switch or move, the further you move along the copper, the more power it creates. So the trend is definitely towards higher integration, with the ultimate goal being a true co-packaged optic with the integrated laser or pump source directly on the chip itself and connecting the fiber directly onto the chip. This is still early in the development. There's multiple paths that can be used. And it's not clear at this point what will be the winning or the final solution. But this can be done by using micro LED, which is a extremely low power LED placed on the chip. The advantage of the LED is, in addition to the low power, it also has a much higher temperature tolerance, so it can handle the higher temperatures right on the chip. This is typically then connected with a fiber bundle, which are large volume packages and bundles of fibers that each fiber is carrying a very low data rate or low amount of data, but it's multi-channel, so it's can handle a large overall volume. This is good for distances up to 5 or 10 meters. Alternatively, it can be using more of a standard, maybe a multi-mode fiber with a VCSEL source. And then there's also some developments using single mode fibers. There's a lot of work ongoing in the industry, startups that are working towards finding solutions for this. The fiber volumes are very large and the prices need to be very low. And that's probably going to be one of the challenges moving forward, is how to create the infrastructure to create such volumes of fiber. If we talk specifically about the LED, micro LED solution, the fibers themselves tend to be very small diameters because they have to fit many of them directly onto the chip. And it needs to be very low cost. And then creating these fiber bundles of these very small diameter fibers is a new technology that really hasn't been done before, needs to be automated much more than all of the testing that I've seen so far. Everything is pretty much manually bundled cables. So that's really one of the interesting paths that I see on the intra-data center connections. If I talk about inter-data center connections, currently there's a lot of different fiber types. You can use standard 652D fibers, the 657A1 and A2, more bend-in sensitive fibers definitely are becoming more and more popular. But looking into the future, some of the emerging technologies definitely are related to the hollow core and multi-core. So the hollow core is, as it's stated, is a hollow, instead of passing the light through a quartz core or a silica core, there is a air core. So it's completely hollow and it's maintained through internal reflection between the air and the glass. The advantage of this, the first advantage is the lower latency. So there's about a 50% reduction in latency because the light is traveling through air rather than the silica. This is a huge advantage. It allows faster communication between from chip to chip. It allows more flexibility in the data center layouts, both in the scale up and the scale out. And it gives more flexibility in the connections even between the data centers. Also, one of the advantages of hollow core is the lower attenuation compared to a standard single mode fiber, which would be in the 0.18 something number, and hollow core can bring it down all the way below 0.1 dB per kilometer. It also has reduction in nonlinear effects, so you can have higher power, higher pump power, so and which gives you longer distance. There's a few different designs on that. There's photonic band gap fiber. There is different designs with capillaries. Currently, most of the research and production is working on this anti-resonant or double-nested anti-resonant or DNAM fiber. So there are a lot of advantages to hollow core fiber, and there would definitely be more use cases. The challenge is the manufacturing. It's a very complicated process. Very precise requirements are needed on the entire production chain, the production of the preform, the drawing of the fiber. It's done at much lower speeds than a standard single mode fiber is done today. But there's a lot of work going on in the industry to increase those speeds, to increase the production, increase the yields. I see this as a very exciting, interesting product that will take over more and more connections in both inter and intra DC connections into the future. Another one is multicore fiber. So instead of a single core, as it said, you have multiple cores within the fiber itself. The advantage of this is mainly in space, that as ducts are utilized or are full, and cable density, fiber densities become higher, being able to put multiple cores within a single fiber just allows more data per space. And then if I talk about the kind of manufacturing considerations, what does it mean for all of these different fiber types? So going from the traditional fiber, we already see that the 657A2 fiber, which is bend insensitive, is gaining more and more traction. This is especially relevant inside of the data centers where the racks and the turning rate and bending radius need to be much smaller. The cables need to be more flexible. Also moving towards 200 micron or smaller fiber, down from the 245 standard today. This is, again, purely a space issue, trying to reduce increase the fiber count within a cable without increasing the size. Also, there's some advantages on the 200 micron with lower material use. Moving into the next generation, hollow core fiber, multi-core, they're more challenging to produce, still need the ecosystem and the standards to be developed around it. But those are definitely moving into the future, very interesting. And then the much smaller 50 micron and below fiber, mainly that's for the co-packaged optics with the micro LED, but there could be other applications for that as well if such fiber could be produced. But now when you start getting these very high density counts, you also need to think about how to identify the different fibers. So the conventional ring marking uses a black ink that is placed on the fiber in a series of rings, 1, 2, maybe 3 rings. Disadvantages of that is it increases the attenuation. Each ring will increase the attenuation in the fiber, and you're limited on the fiber ID combinations. With Nextrom has developed a new approach with multicolor marking, where we are using a UV curable ink with different colors, where we're able to mark the fibers or color the fibers with different color combinations. This allows for much larger combinations. So instead of the 36, we're now more than 480 different fiber ID combinations. Also, it reduces the attenuation increase by over 95%, and it can be run at much higher speeds. So now with these high density cables, we have more identification options. The other main movement that we're seeing in the market is going from traditional fiber ribbons to a rollable ribbon. The rollable ribbon has intermediate bonds. Instead of bonding the entire structure of a flat ribbon, there's just small glue points between the fibers. It allows the fiber to be kind of spread, but it gives much better rollability, and it allows for very high density fiber counts. And when thinking about the requirements on the equipment for a rollable ribbon machine, it needs to be very flexible. It's a very IP dense space. There's a lot of patents on the different designs, so the systems need to be flexible. The ribbon, or the bonding needs to be strong enough, but not too strong, that you can still separate the fibers, and you need to be able to run as fast as possible. Once you get the rollable ribbon, then it needs to be put into a cable, and that's first done by bundling it. So the ribbon is rolled into a bundle where you have these individual bundles that allows you to better identify the different fibers. So you have individual bundles within a larger bundled cable. And then moving into the super bundling, where you take the individual bundled cores and put them into a very high density, high fiber count cable. So cables can be well over 10,000. We show 13,824 fibers. There are even larger cables with a 4-centimeter diameter. The manufacturing considerations on this is it needs to be very precise in order to maintain the tension and proper bundling within these cables. And especially with such high fiber counts, any variations in the tension will affect the attenuation and possibly even damage the fiber. So the equipment needs to have very precise tension, closed loop control on all of the different processes. And then the final process is the fiber jacketing, which can be for low smoke, no high halides for internal or inside buildings. There's a lot of different materials and that can be used for the final jacketing. Also, the premises cable for data center scale up and scale out. It's bringing the high density structures inside the data center. So again, these need to be very high density, small diameter cables, many fibers, maintaining a flexibility so that it can be routed within the data center while maintaining, without increasing the attenuation or damaging the fiber. So in summary, overall data centers, both inter and intra, are moving away from copper towards fiber optics, getting closer, the fiber optics closer and closer to the chip. The fiber designs or the cable design is going to have smaller diameter fibers, new fiber types, such as hollow core, very small diameter fibers, multicore, that will be packaged even together inside of a single fiber optic cable. And this requires a full consideration of the production environment, manufacturing ecosystem, from the glass itself all the way through fiber identification, testing, and fiber optic cable production. And just a little bit about Rosendahl Nextrom. As I mentioned, we are the equipment manufacturer, so we do have the equipment for the entire process from preform manufacturing all the way through fiber draw, post draw, and fiber optic cable. We kind of can be a one-stop shop for anybody working on developing optical fiber production.
Thank you very much, Kevin.
Thank you.
That was fantastic. That was really great hearing from you. We really appreciate all of the fantastic information that you've just shared. So thank you very much. I'm going to hand over now to François. François, do you want to take the floor for the last session?
Yes, of course. Thank you very much, Kevin and Mitch. Excellent presentation. I will now share my screen. Share, and here we go. You can see my screen, I'm assuming. I hope so. Display. Here we go. Okay, so we saw a lot about what's coming up for fiber, what are the new equipment like switching, introducing 800 gigs. So I will address some other kind of drivers, but it will actually go along with what Mitch and Kevin mentioned. So it's improving quite fast. Bandwidth is improving, actually increasing. Latency demand is quite also there for AI sharing memories. I'll talk about that a little bit, and of course, how you manage to test all this. High fiber counts, like mentioned, it's like getting a lot of fiber counts and ribbon type fibers. For example, in this one, there's like a lot of ribbon together in the same cable. It looks like a copper cable, but it is in fact a fiber optic cable. So this is getting a lot of connectivity happening in the data centers. Local fiber, like mentioned by Kevin, is now becoming quite interesting to save on latency and attenuation. Multicore fiber also being introduced into transceivers, really interesting to actually accommodate 1.6 terabit per second transceivers. So transceiver, yes. So cooling is becoming an issue starting after 800 gig. Cooling is becoming important, as you may have tens of thousands of transceiver in few racks. In the entire facility, you can have 100,000 transceivers, and they may fail. There are studies mentioning 1 to 2% transceiver failure rate per year, and the cost is around $20 million to fix them, because you have to search, and because they are not failing totally, they are in fact having intermittent issues. So it's very, very difficult to find where they are. So hopefully AI will help us to identify where there is actually intermittent condition into the network. Open architecture, Mitch mentioned it, as you have now the possibility to disaggregate infrastructure, so you can use anybody from any vendors introduce into your own switch vendors. So it's like everybody has to work together. In the past, you had to buy the same ecosystem from the same vendor. Now you can mix and match. And there are interrupts happening in the world between all these vendors to make sure they are all working together. And it's actually really nice to see the community working along like this. Bunch of experts are getting together and making sure it's all working. Network automation, AI-driven system. That's where we're going. It's much more an assistant at the moment, but eventually will take over system integration and signaling. What is signaling is when you want to create a path between site A and site B, but it's already being used by other type of traffic. You want to make sure that the bandwidth usage is dynamically allowed or managed. And then you make sure that all this data is secured without any errors. So AI will take over in these aspects of managing traffic flows using LACP type of aggregation protocols and all kind of other IP protocol to help you improve the performance of these specific links. AI generated video as well. We are seeing a lot of end users at the other end creating their own mini data center where they are providing streaming of their own content. And this is like changing the game because now the data is not coming only forward, it's also coming upward and going towards the data center. So it's in bidirectional way. So we're seeing a lot of load balancing going back and forth. And all these contents are coming from millions of different sites. And they are actually going through the data center as they are generating the traffic. And then from the data center is distributed to everybody. Network evolution now. And as we see, the data interconnectivity is increased now to 800 ZR. From campus to the regional gateway or the network service provider. They are actually providing the connection to the other sites. But there is also campus to campus connection happening where they can have now holocore fiber, such as holocore now is nice to use because of the latency saving. You can now share the RAM, the memory. And that, as you know, the memory is becoming an issue as it's expensive, it's difficult to get sometimes, and it's spreading quite fast. So in order to have better RAM into, let's say, a facility like a campus, then why not sharing the RAM or the memory from the other campus? So why not installing a low-core? A low-core fiber will allow you to share that memory. Co-package that was introduced by Steve is one example. You want to actually be able to have this chip, which has a co-package optics connected to the other one into the other side. Why not using holocore? Because holocore has a lower attenuation and better latency, 30% actually better latency. Yeah, connectivity. Now, the connectivity is like becoming quite a challenge because what tools do you need? Do you have LC connector, SC connector, MC new connector? Do you have LPOs, MMC, so multi-core and holo-core? Do you have adapters? There was a question about an adapter. Yes, there are adapters. You can have the LC adapter, SC adapter connected to your holo-core. So are you well equipped to test all this? So connectivity, so meaning new connectors and density. So in the past, we had dual LC, for example. Now, why not having MDC? So in the same form factor, instead of having two connector, you have 6. Or if you have an MPO, why not having MMC and having 3 times the capacity for the same connector size? Now, you can see the challenge going now on these different data centers. You have to be a little bit uniform. If you go with SN and then MMC and then LC and then MPO, it's quite complicated for a technician to handle all this, to test all this. And that's something that I will address in the coming slides. So looking at DCI connection a little bit deeper in terms of testing. And as you can see on the diagram here, you have a campus connected to the metro core. And this specific one is using holo-core fiber. Now, holo-core fiber, how do you test it? So there are OTDRs now from EXFO, obviously. You can test them. You can test actually the same thing as you were being testing fiber in the past with OTDRs. Same principle. It's just the way we are doing the analysis on the holo-core is different, but it's been done. And you can see the attenuation and where you have splices. Because believe it or not, you can splice hollow core fiber, but you'll see it on the OTDR trace, and I'll show you that. Multicore fiber is, like I said, being introduced into the transceiver. So are we inspecting them? Are we cleaning them? How do we manage multicore is also something that is has to be addressed. You can monitor the fiber because all these fiber will increase, like mentioned by Mitch. So a lot of and Steve, a lot of fiber distribution. So why not starting to monitor those fiber and then having AI predicting degradation? For example, between the metro core and the data center, you have a fiber degrading. So you know in advance where the problem is. So you can send a technician to the specific spot and then fixing the fiber before any complaints from other data center or other enterprise or web scale. And then you fix the issue. So better system will provide you better business. As you have a solid network, you can provide a prime service at a fantastic price and then challenge your competitors. So of course, obviously, there's a lot of transceivers. So I'm showing transceiver. I'm showing the new OLS system mentioned by Mitch. It's pretty nice because they are compatible with all kind of transceivers, but these transceivers, they need to be tested. Hollow core fiber, I showed you a link, of course, of hollow core fiber. What's the purpose? And I'm going to go into the details as Steve mentioned it, but 4.6 microsecond per kilometer, very nice latency. We're talking 30% faster propagation, so that's excellent. And then 0.06, we have been testing attenuation to 0.06 dB. That's per kilometer. That's fantastic. So it's getting better and better. The preform mentioned by Steve is quite a or Kevin. Sorry, I'm saying Steve. It's Kevin. Sorry, sorry, Kevin. So mentioned by Kevin. It's in fact very important and very difficult to manage the preform and to create the fiber. Hyperscale DCI obviously is the main focus. And I saw one of the question is where can I test hollow core fiber? How do I do the testing? So the best thing is to get you a spoil of hollow core fiber from one of the vendor. And if you want to test it, we have an EXFO, of course, the gear to help you with that. But other products are available on the market. It can be addressed later. Now, testing the AI-driven network. Now, before it's fully driven by AI, it will be an assistant. But introducing AI, you need to make sure the low latency, the performance stability, the low packet delay variation, which is the jitter, and interrupt. So let's look at the DCI operation. It's a little bit complicated, but make it very simple. You have the OTN links with mux-demux on the bottom side, where you're actually multiplexing, all these different rates. So 100 gig, 400 gig, 800 gig over the same fiber. And then it's demultiplex and then OTN system. On the top one, which is IP over DWDM mentioned by Mitch, then you have directly the router connected to that open line system and then sending the traffic again mixed together with others to that DWDM system to the other end. So you're excluding out of this equation the OTN switch. So it's an advantage and a disadvantage. So there's two mindset on this. And then you have the hollow core fiber, which can be connecting that OLS to the mux-demux of the other collocation. That's something we are seeing, and that's something we are testing at the moment. So we are testing hollow core fiber basically for latency, jitter, and of course throughput. But overall, with the OTDR, you make sure that it is actually without any extra loss. AI also will recommend some action. So the technician will be able to see what's the link capacity, what's the overall health of the DCI links? What are the wavelengths in use and what are the rate associated with the channel? At the moment, the technician is a little bit blind. He has a work order that tells him basically this is what you need to test. The operation manager has a little bit more an overview, but eventually all this information will be available for the technician to be able to test correctly and which one has to be addressed. So instead of testing all over the place, you'll be able to actually test correctly the right system and the right signal. Now, we were talking about multi-fiber testing. There's a lot of multi-fiber, and now they are within the transceiver. So with a fiber inspection probe, like the FIP 500, you can inspect inside the transceiver these little cores and find out the ones that are dirty. And then you clean. Don't clean without inspection, because if you do, you can actually add dust to the core itself if it was not dirty at the beginning. So inspection first and cleaning after, always the principle. 80% of all problems of every network for the last 15 years has been fiber cleaning or non-clean issues. Now, multicore. We were talking about multicore. Now we are seeing them on the transceiver. So the same transceiver may have a multicore fiber into a multi-fiber connector. So you say, wow, okay, there's a lot of possibilities. So instead of having only one fiber core, we have multiple core. So in that specific one, we can send 4 times 100 gig, 4 times 400 gig. And now you see where I'm going. We're going from 800 to 1.6, and we are already testing 3.2 terabit per second. I have demands already for 1.6 terabit per second links. So now if you're using these transceivers, which exist and available today, now you need to make sure they are not dirty. They are tough to align. Some people, they were maybe asking, how do you align them? There is a rotation marker on these multi-core. So when you are having, you're creating, let's say, a fiber connector, you're making sure that the rotation marker is well aligned. Also, the way we're transmitting and receiving is different. So you don't actually send to transmit on the same side. So because of a co-channel distortion, because the light may be, traveling across the core a little bit and then migrating to the other core. So that's the problem with multi-core. So you're actually transmitting from one side to the other and then receiving the same thing. Okay, so testing transceivers. Now, like I said before, there's thousands and thousands of transceivers, all kinds. But now we're going into QSFP-DD, OSFP, OSFP RHS. There's all kinds of transceiver coming out at different rates. Now, I was at a customer 3 weeks ago. The guy had a box. He say, hey, those are 400 gig. They don't work. So we put them into a test set. We loop them together, and then we validate if it's working. Actually, it was failing. What we did inspect the fiber with a microscope. We saw it was dirty. We cleaned it. We tested again, and everything passed. The optical level were back to normal, and then it was back functional. So the guy said, wow, let's try another one. Same thing. And let's try a third one. Same thing. So the guy said, oh my God, so we did remove them without cleaning? Hey, maybe. And then there's also a lot of AOC cables out there. We can do the same thing. You have to validate them before installation. So there's a lot of thinking about that. Are we testing the AOC and transceiver before deployment? Because in an AI-driven, everything has to be clean. Everything has to be validated before, because otherwise it's very nice having an AI-driven system. But if you have issues already with transceiver, it may be failing because of a dirty connector on a transceiver and not because AI algorithm was not set properly. So this is really important to make sure that everything is clean out there. Every transceiver has been tested before deployment. It's a lot more expensive to install. But remember what I said about the study about having 1 to 2% transceiver error rate per year? That's $25 million repair cost for, of course, a 100,000 transceiver facility. Now, the hollow-core fiber. We said before we need to test the hollow-core fiber, so you are using a regular OTDR. The hollow-core fiber, you don't test directly. There's always an adapter. And in this case, it was a SC2 hollow-core fiber. So you're connecting your SC to the OTDR. And that's what you see in the gray zone is the single mode fiber. And then you're dropping quite a lot because this is the transition from single mode fiber to hollow-core fiber. And then you have the gas filling event, because there is inert gas into the hollow core. But when you are fusion splice, you have to cleave it. So the gas is like basically the fiber sucking air inside. And then you have this effect on the OTDR. So you like bumps. So what you need to do, you need to test in both directions. And in both directions, you are eliminating these bumps, basically that gas effect on the OTDR. And then you have a nice trace showing you where the splices are and where you need to go to address a specific excess loss, for example. So the usual method to test fiber is now in place with EXFO. So you can use the EXFO OTDR with the hollow-core fiber software. And then you can see where the different losses are. Now, link performance validation in an AI-driven or into a new system. First off, you need to validate links. So most of the time, we call them transport testing or Ethernet over OTN or transport Ethernet. All kind of different wording to say the same thing, that we're transporting data from the network gateway, for example, to the co-location data center. So it's a DCI, it's a data center interconnection via a network gateway. So you're mixing basically that new channels among others. So we have to validate the connectivity, the performance, interrupt, automation, and scale validation. So because you want to make sure you're able to scale it up to 1.6, 3.2, and 6.4, and so on. There's already discussion about 12.8. So it never ends. Then you have to validate also if you have now the new open line system with AI management. So we call it IP over DWDM. Then you need to validate that. And at the same time, here you see the non-coherent, the coherent type transceiver, they can be validated at the same time. So you're validating here the transceiver, the optical link, and the DWDM system in one shot. Now, if you have issues, then you have to go and isolate the trouble. Unfortunately, at the moment, the AI cannot tell you, eventually it will, or maybe it is already, but I didn't see it yet, that the OLS has a problem on the transceiver. To be able to do that, the OLS has to be interrogating the transceiver with the AI. So the AI would say, oh, that transceiver is telling me there's an issue on the optical level. Now, this is where we're going, but it's really the beginning. So transceiver will get more intelligence as we go. And so are the switches. Now, at the moment, you can do some test automation. So you can drive these tests continuously. So what you do, you have a simple traffic simple. So not very fast. Let's say a 10 megabit per second link, always continuous between 2 points. And then you are activating your AI. So AI, let's say in this case, will migrate the traffic from site A to site C, but it will go site A, site B, and site C. This change will have some impact. So you want to see what's the impact on the bit error rate and what's the impact on the frame checksum error rate. So, or other types like latency and jitter, anything can be actually monitored. So this is something that is happening right now. So people are doing it at the moment. So this is a real measurement we've been doing. So this is a continuous test. Um, there's many people out there doing all kind of automation. Really interesting. If you are interested, you can always communicate with EXFO or with Mitch or Kevin to have more details about these things. The impact of a network change. Now, I'll go fast here because time is flying. The impact of network change. So you have a change, let's say, in the network. So you are actually activating a new link. So you want to see what's going to be the impact on your data. So it can then have some impact on the receiver power. It can have an impact on frame checksum issues, so having frame loss. And this type of monitoring can then show you, okay, we have now a power issue because the AI did change something in the link. Why we have a loss of power suddenly, which is not supposed to happen. FEC is getting crazy, correction all over the place. So this is something that can be addressed with testing. Finally, almost finally, but you can also analyze that 1.6T you're just putting into the network. You want to validate the signal to noise ratio and do some wavelength tuning and power control to see how it is behaving amongst the others. And you can, of course, measure FEC. You can measure CD, PND, OSNR, all this from the transceiver itself, because the transceiver provides what we call optical matrix. And all this kind of measurement can be available straightforward from a test measurement platform. CDPND are issues. I won't address to that too much, but you need to make sure chromatic dispersion and polarized mode dispersion are measured at installation level. So when a new link is installed, make sure this is measured, because dispersion will impact the traffic and you'll have bit errors. And finally, with AI, you should have now fault detection within minutes, fault isolation in 2 hours instead of days, repair operation hours. That is still a behavior that you need to address. Service validation obviously takes minutes now, 2 hours. A day can still be done, but now we have a tendency to do it a lot faster, so up to hours, few hours. And specific matrix has to be analyzed. And that's it for my part.
Thank you very much. Thank you, Francois. That was excellent. Some great detail in there, and we've had a lot of questions come through actually in the last hour or so. So we're going to do our best to answer as many of them as we can in the time. We have got a little bit of extra time. We're not going to be thrown off the platform or anything like that. So please don't worry. So Francois, while I've got you here, I'm going to ask you a question. You mentioned AI just now. Will AI reduce network testing, or is it just going to change what we're testing for?
That's a good question. In fact, AI is supposed to help you reduce the hours, I call it man hours, to test a trouble, because it will identify an issue already. Like the fiber monitoring system, for example, will provide you some information about where the problem is happening at the moment before it becomes a real issue. So you can send a technician to the right spot instead of driving all over the place. So yes, it's supposed to. Now, there are some of the things you need to test always. You cannot exit it. Yeah.
Thank you very much. We've had a question come in. It's one for Kevin. Which companies have experience and personnel nationwide with maintenance of hollow core fiber for long distance? I beg your pardon.
I would say that at this point, there's probably not many companies out there that are fully developed in the market for testing. The hollow core deployments are still quite new, so the full maintenance and ecosystem, I don't know if Francois may also have some ideas on that, but in my opinion, it's still a developing market. And with the amount of hollow core fiber that has really been deployed, it's still quite small, or extremely small if we think about compared to single mode fiber.
Yeah,
Yep.
absolutely.
I agree.
Go on, Francois. Sorry.
No, I was just agreeing. It's yep.
Excellent. It's a live debate. It's nice when people agree.
Yeah, that's right. Of course.
Fantastic. Thank you very much. So one for Mitch. How should operators weigh adopting the newest optics, coherent optics, against protecting existing investment, would you say?
Well, that's a big challenge. We know lots of operators, again, can't just abandon their, legacy equipment. They have to, grow into the new, support the new demand, but maintaining the legacy. And that's where some of the thing, and unfortunately, I didn't get into much more detail. But one of the things that are, these new disaggregated thin transponder approaches is actually the ability to support both legacy interfaces. So the world isn't going all to coherent, and I think my colleagues here can speak to that. I mean, so we have ability. The nice thing about thin transponders, you can take some legacy, say, router with older grayer optics, support that in with some of the newer coherent, and then multiplex that into coherent. So I think that's the beauty of it, is it is a really nice way to bridge kind of the old and new worlds together. So absolutely.
Fantastic. We've had another question come in. What are high capacity termination configurations for high cap cables inside a data center? Who wants to go first with that one?
I think that Francois touched on that with the CPOs and the high density CPOs, even with higher connection point per volume. So I think that CPO is one of the main. I'll admit that this isn't my. It's a little bit out of my knowledge base, but I think it also depends. It depends a lot on the available loss, what your loss calculation allows for. There's so many different positions and connection points within the data center that it's really a mix depending on the requirement. So there's not just one way that dominates everything.
Thank you. We have had quite a few questions in about hollow core and multi-core fiber as well. Someone's asked if multi-core fiber has a future, and somebody has also asked about fiber splicers for hollow core. Do they need will they need a separate splicer? So I guess that's kind of for you and a little bit for Francois as well there.
Well, if I first talk about if multi-core has a future, I would say definitely.
Yeah.
I think all of the different fiber types have a future. There's no single requirement that will cause one. Maybe hollow core has a lot of advantages, but the reality is that the production volumes are so low that it's not even closer. It's many orders of magnitude that have to be increased in order to meet the demand. So in the short term, there's going to be a mix of standard 652D fibers, 657A2, but also multi-core has a place in that because of the higher density, and also the fact that multi-core is more advanced in the specification and ITU requirements. They're working on making more standard, but it's much easier to make a specification and a requirement for a multi-core where you have a kind of a standard core. It's more on the spacing and the crosstalk that have to be defined, where hollow core, there's many different hollow core designs. So making a single specification for hollow core is going to be a challenge. And I think what the hollow core manufacturers are going for is trying to be the first, dominating by deployment.
Yeah.
By being the first one out, they will become the defunct standard. But I think that multicore definitely has a place, and especially over the next 5 to 10 years, there's no way that hollow core or anything else could dominate the market.
Yep, I agree. Multicore first, it exists already. Like I said, the 1.6T transceiver, you can find them with multicore at OFC show. Corning was displaying one of the multicore, so it's available on the web if you need some information. As holocore, I was talking with an expert at EXFO, and he said holocore, the beauty of it is if it's you have 1,000 kilometers of fiber, you would use it without any amplifiers. So that would be great because the Fresnel and Raleigh backscattering is not happening in holocore as we think. It's completely different. So then the amplifiers can be used way further down. So the holocore would be, when manufacturing process will be managed correctly, then it can be used for submarine system. Like, wow, this will help quite a lot. Yeah.
Yeah, it's one of the holy grails of multicores to go to the really long, say, 1,000-kilometer length fiber. Then
yes, yeah.
Fantastic, thank you. We are running slightly over, so apologies to anyone who sent questions in that we haven't managed to get round to answering. We will pass these on to our lovely panel after the debate has finished, after the broadcast, so we can still get some answers for you guys for those. So just to reassure you, we haven't forgotten your questions. But I just wanted to reiterate my thanks to you guys for joining me today. Mitch, François, Kevin, it's been an absolute pleasure listening to and talking to you. It's really exciting times. I'm looking forward to seeing what kind of comes next. So thank you very much. We appreciate you joining us. Thank you very much also to our audience for joining us today and for sending in so many questions and engaging with us so much. It's really fantastic when we do an event like this that we know it's hitting the mark with you guys. So that's great. A couple of little reminders and answers to a few questions that came in. Resources, presentations can be available after the broadcast. So please feel free to have a look at the resources section. The broadcast itself will be available on demand after this session, and it will be at the Fibre Systems website. So that's www.fibre-systems.com. And you can also, as I mentioned at the beginning, request a certificate of attendance as well. So without further ado, just offer my thanks again to Mitch, Kevin and François. Thank you very much to our production team working hard in the background to make sure this happens, and to everyone who's joined us today. We'll see you at the next one. Thank you. Bye-bye.
Yeah.
Thank you.
Bye, everyone.
Bye.